So I'm going to talk about work we've been doing at the Francis Crick Institute. First thing to say is that the association of air pollution with lung cancer is not a new observation. This is something that's been established really over the last 2 decades. What we don't know, what we didn't know until fairly recently to this work, is whether air pollution directly causes lung cancer or whether there was something more proximal in the sort of upstream pathways driving cancer. And I think what this work shows is that air pollution is directly causing lung cancer, but through a slightly unexpected pathway. So to really understand how environmental carcinogens cause cancer, we have to sort of review the models of cancer initiation. And this is a classical model of cancer initiation. If you asked me 2 years ago how did cancer start, I would have said to you, environmental carcinogens cause cancer by causing mutations. Mutations in DNA result in driver genes that expand individual subclones or clones of a tumor, and the tumor starts. Well, that's a classic model, and of course, that's typified by tobacco carcinogens that generate C to A mutations in DNA and derive the classical mutation G12C in KRAS, for example. Ultraviolet light does a similar thing, mutates DNA, and diseases like lung cancer and melanoma have a very high number of mutations because of the impact of the environmental carcinogen on the DNA. But there's some major problems with this model. First of all, we know from work from the Sanger that we are essentially a patchwork of clones harboring cancer mutations in our normal skin. So this is a picture of an eyelid. There are multiple clones on this eyelid that harbor cancer mutations, but there's no evidence of cancer in the tissue. So that tells you cancer mutations may be necessary for cancer initiation, but they are not always sufficient to drive cancer. And then added to this, a year and a half ago, Alan Balmain and Reaver and colleagues published this beautiful paper looking at 20 IARC class 1 carcinogens in mice, and they showed the vast majority of them, 17 out of 20, did not induce mutations in DNA. And last but not least, another spanner in the works of this model is that the common BRAF V600E driver mutation in melanoma is not an ultraviolet light-induced mutation. So this brings me to lung cancer in never smokers. This is a disease also of low mutational burden. So we know air pollution is associated with lung cancer, but what we don't know is whether it directly drives it. So if it directly drives it, any explanation for never smoking lung cancer would have to fulfill 3 criteria. 1, it would have to explain the geographic distribution of the disease. 2, it would have to prove causation. And 3, it would have to explain how cancers can be initiated without directly causing DNA mutations. So for air pollution as a cause of lung cancer, we'd have to establish cause, we'd have to establish a geographical variation in pollution levels with never smoking lung cancer, and we'd have to demonstrate how air pollution causes cancer without causing mutations, and essentially reneges on model 1 that I showed you. So that brings you to model 2, and this is the fascinating part of the presentation because this is work that was first published by Isaac Berenblum in 1947 that we've somewhat forgotten. And this is his tumor promotion model. And he said you need 2 steps to starting a tumor. 1, the initiating event, which we now know is probably mutations, and 2, the promoter event. But you need both. And neither one nor the other is sufficient to drive the cancer. And he showed this in mice, giving mice DMBA back in 1947. We now know this is a mutagen. He didn't know that at the time. That creates a low level of mutations in the skin, but that does not drive cancer. It's only when you add the TPA at some point after that, 2 weeks, up to 52 weeks after the DMBA, that you get clonal outgrowth. And we show in this presentation this afternoon that this is how pollution is working. Now, the interesting thing about this is that we have, in terms of the initiator, the mutations present in normal lung tissue. So in half of biopsies, we can find activating mutations in KRAS, in G12, codon 12, codon 13, codon 61, or EGFR in exon 19 and to 21. And so these are pre-existing mutations. They exist in our normal tissue, in histologically normal lung tissue, but there's no evidence of cancer. Now, if you inhale pollutants, and we show this in our mouse model, we show that giving mice air pollution increases the number of tumors, the grade of tumors in our mice, where we can stimulate an EGFR or KRAS mutation early on in these mouse lung epithelial cells. You give mice pollution. This induces interleukin-1 beta that transdifferentiates the epithelial cell into a progenitor cell. And it's only if that progenitor cell happens to harbor an EGFR mutation that was present in the normal cell, in the normal tissue, that the cancer can expand. So we show in the presentation this afternoon a close correlation between the geographical distribution of PM2.5 particulate pollutants from diesel exhaust, combustion of fossil fuels, with lung cancer incidence in never smokers. We prove causation, so we show that in 3 different mouse models, increasing levels of PM2.5s lead to more tumors and more aggressive tumors. And we demonstrate that pollution can conform to the Berenblum model of tumor promotion by demonstrating that interleukin-1 beta is released that causes differentiation of cells into a stem-like progenitor cell that with an EGFR mutation drives tumor initiation. And central to this is that we can treat mice with an anti-IL-1 beta antibody and block tumor initiation in response to pollution. And of course, this reflects very nicely the CANTOS data that I mentioned yesterday with canakumumab, an anti-IL-1 beta antibody shown by Novartis in 2017 by Riddler and colleagues in New England Journal that reduces in a dose-dependent manner lung cancer incidence. Now, we didn't know how that worked, and I'm pretty confident this is one of the signaling axes that anti-IL-1 beta antibody works through to prevent new lung cancers in patients treated with canakumumab.